Good evening, everyone. I'm a graduate student from Dartmouth College, and I work with Biological. Today, I'm going to talk about the effects of outflow on stored and reincarnate energy. First, introduce. Well, I use a single fluid LFM coupled with RCM. I think that William spent a lot of time to discuss single fluid versus multi-fluid. Basically, personally, I agree with you. But at this point, since the LFM, multi-fluid LFM, is not available, and so I first use this. But this is definitely not to say this is worthless. We know that all MHD global modeling is quite different in many aspects, in grid cell layout, in boundary conditions, and in the way that's coupled with the reincarnate model. So I think that at this point, we definitely worth trying this. And when the multi-fluid version is available, and we tested this in the multi-fluid version. But of course, we need to be cautious about the result we get here. Before we draw any solid conclusion, we better wait the multi-fluid version. Okay. Here is the introduction about the method I used to edit the outflow. I first specify a constant exobase, which at the altitude of 800 kilometers. And I assume a Maxwellian distribution, and I use the review theorems to calculate the upward part of the distributions along the magnetic field lines. And this plot is an illustration of how that field lines values is interpolated back to the LFM ghost cells. And there is one thing that I only added this outflow above 60 degrees latitude. There is a reason why I choose this is two. One is that below 60 degrees, that's a domain coupled with RCM. I do not want to do some strange things in this region. And another thing I will talk about later. Okay. Here is a plot. The top panel is a plot of the reincarnate energies. And the bottom ones shows the IMF-BZ component. The first 4 hours is basically 2 hours southward and another 2 hours northward. This is kind of LFM tradition, basically to feel the magnetosphere. And then we do 6 hours minus 15 NT, and this is kind of build the reincarnate. Interesting thing is like this. Oh, I forgot to introduce you about this. The red line is that with RCM loss terms off. In RCM, there are several built-in loss terms representing the charge exchange and pitch angle scattering, the tactic. And the blue line is just with these loss terms on. We can see interesting thing is that after the 10 hours, I turn it back. Both curves drops. This is very interesting, and the slope is almost the same, which means what? Means that in this case, what really dominated the loss is neither the charge exchange or the pitch angle scattering. There are some other mechanism we do not consider here. Here is the outflow run, which I added my outflow to the LFM RCM. You can see this looks much better for me, and because you can see the loss terms off after the IMF flips back to northward. That remains almost the levels off, which means no loss. And in the loss terms on, which is a blue curve, and that curve drops, which means in this case, what really matters is the RCM loss terms of pitch angle scattering and charge exchange. So what caused this? I plotted the, this won't work. Would you mind to switch back to the PDF version? Okay, sorry about that.
Sorry about that. Well, we're taking a technical timeout. The next speaker is listed as Paul Song, and we're not sure. It was either Paul or a representative able to make it. If not, then Roger Varney, you may want to mic up. Okay.
Okay, here we got it. Basically, here I plotted the entropy, and here I loosely use the terms entropy, by which I actually means that the flux tube conserves the quantity of A's, which is, I think, given by Johann Böhm in his 2009 paper. And this is not the actual entropy, but closely related to that. Because in this case, we only care about the patterns of the entropy. The value is not that important, so this is a very good proxy for the entropy. The left is a baseline run, and the right is an outflow run. We see that at this point, maybe Roger may ask me, why the outflow run and the magnetopause, they're even smaller. And in the previous study, people all see that in the outflow run, the magnetopause may inflate it, may stretch. This is because what I just mentioned before. In this LFM RCM coupling, when the RCM density is coupled back to LFM, the density is modified. It's fitted to a Gallagher plasma sphere model, which means in the inner magnetosphere, we have the same effect of added some cold plasma component, which represented the plasma sphere population. And in the previous study, to my best understanding, none of this study added this part. And here, we see the left one. You see this low entropy flow channels, flow scene, which means the interchangeable, unstable is interchanging stable. And which means that the plasmas in the inner magnetosphere, they may diffuse out. I think that's because this diffused out plasmas actually stretch the magnetosphere. Also, of course, we have the polar wind outflow plasma, but the density of the polar wind outflow plasma compared with this diffused out plasma sphere plasma, that's really small. So that's why we see this one actually stretched more. This is my explanation. Okay. Another one shows the field line tails. You can see that again in the outside ones, the X line moves earthward, and in the baseline run, it's located at around -30 RE, and in the outflow run, it's to, I will say, between -20 and 25. Which one is better? It's difficult to say at this point. Please remember this is a -15 case, really strong storm case. And here, I basically placed some testing particles in R equal to 3.5 RE and equally distributed that. And I traced how these particles will evolve and finally end. The left one shows you the baseline, right one is outflow. You can see that more particles diffused outward and drifted to the tail. And in the outflow one, more particles is confused, is confined within the 6.6 RE. The green circle means the 6.6 RE. Okay. And here is basically the statistics of the previous plot I showed you. You can see that clearly in the baseline one, more particles diffused out, and in the outflow one, more particles stay within. Finally, I do study an event of the 1999 October 22nd storm. You can see very interesting is that the top panel is the rain current energy, which I integrated within the 6.6 RE region. And the bottom panel is the peak energy density of the rain current. And why the peak density is higher in the outflow one, but the total energy is the outflow one is one. This is kind of interesting. My explanation is like this. With stronger interchangeability, which means enhanced plasma injection from tail, which means low entropy bubbles or channels can penetrate deeper into the inner magnetosphere, which have the potential to generate some high energy particles. But these particles may diffuse out very fast. So that explains why the peak energy density is higher, but the total energy is lower. Okay. So this is basically a summary. As I mentioned before, I better wait the multi-fluid version. Okay, thank you.
Two quick questions. One is in the LFM, do you have co-rotation turned on?
I don't think we turn on.
Okay. And then another question that you may not be able to answer, but I'll try.
Yeah.
So typically in LFM, people, please correct me if I'm mistaken, but typically in LFM runs with the northward and then southward pattern in idealized runs, you're doing that to build up a little mass inside the magnetosphere.
Yeah.
When you have the outflow turned on, is that necessary because during the quiet time you could build up ionospheric mass in the magnetosphere? Have you taken a look at that?
Oh, that's not necessary. I have another run which is without the first 4 hours, which shows basically the same pattern. Yeah, but I don't show here.
Excellent. Okay, any other questions before we move on?